3 in the morning, September 3rd, 2024. A radio astronomer sitting in Perth, Australia, is staring at her computer screen when something absolutely impossible happens. Not something she didn't expect to happen eventually, something that shouldn't be possible at all according to the laws of physics. The signal appears on her monitor. It's subtle at first, just a small blip that emerges from the background noise like a whisper cutting through static, but her system flags it immediately. The algorithms she's programmed recognize it for what it is. Fast radio burst, FRB. She's seen dozens of these before over her career. Hundreds maybe if you count all the faint ones. They come from nowhere in the cosmos. They last about a millisecond, then they're gone forever, vanished back into the noise. This one is different though. She doesn't know it yet, but this one is going to keep her awake for the next 48 hours straight. This one is going to change everything. She runs the standard protocol immediately, checks all the instruments, verifies that nothing is broken, calls her colleague stationed in South Africa on the other side of the planet. Hey, did you see this? Did your telescope catch what just came through? 3 minutes later, the answer comes back through email. Yes, we saw it. Same exact frequency, same exact signature. Both observatories locked onto it perfectly. That's when her heart starts racing because her pulse quickens, and she realizes what this actually means. Because both observatories caught the signal simultaneously. Not close, not approximately the same time. Exactly the same time down to the microsecond. That means it's real. Not a glitch in the system. Not instrument error or calibration problems. Not a cosmic ray hitting the detector the wrong way. Something in space, billions of miles away, just sent a signal, and two different telescopes on completely opposite sides of the planet received it at precisely the same moment. But here's where it gets genuinely strange. Here's where the astronomer's hands start shaking. The signal repeats. Not once, not twice, not 5 times. It keeps coming back. Every single time, exactly 3 minutes later, the same pulse comes through again, like a clock, like a heartbeat. She runs the test again, then again, then again, 17 times over the next 6 hours straight, 17 times. Every single repetition is identical down to the microsecond. The frequency is the same, the intensity is the same, the shape of the wave is the same. It's so perfectly identical that at first she wonders if she's looking at a recording playing on loop. But no, these are fresh detections coming in real time from space. Nature doesn't work this way. This is the fundamental thing nobody understands. Nature is chaos. Weather patterns are chaos. Earthquakes happen randomly. Stars explode without warning. Animals behave unpredictably. Cosmic radiation arrives in random bursts. But this is different. This is a rhythm. This is a pattern. This is something that follows precise mathematical rules. And that changes everything. By noon that same day, 3 more observatories around the world have independently confirmed the signal. By evening, astronomers from 7 different countries are watching the same signal repeat over and over and over. They're comparing notes. They're running calculations. They're all asking the same question that echoes through their research institutions. What the hell is sending this from space? By the next morning, the discovery has gone viral throughout the scientific community. Emails are flying. Physicists are pulling all-nighters. Teams that have been rivals for decades are suddenly working together. By evening of that day, the story breaks to mainstream news. Within 72 hours, there are over 1 million theories floating around online. Some of them are reasonable, some of them are absolutely insane. Someone on Reddit suggests it's an alien civilization trying to communicate. Someone else on Twitter insists it's a message from God. Someone posts a long video claiming it's a government cover-up from Area 51. But here's the thing that keeps even the most experienced astronomers awake at night. The reasonable theories, the ones grounded in actual physics, don't actually explain what's happening. They don't explain the pattern. They don't explain the precision. They don't explain the mathematical perfection of the repetition. They don't explain why something billions of miles away is apparently sending a message that repeats every 3 minutes like the most reliable clock ever constructed by the universe. This is the exact moment when everything changes, not just in astronomy, not just in physics, but in how we think about the universe fundamentally, in how we think about whether we're alone, in how we think about our place in the cosmos. Because if this signal keeps repeating like this, if it continues with this level of precision, that means something alive is sending it, something with intelligence, something with technology, something with power. And the biggest question we can ask isn't what it is. The biggest question is why now? Why September 2024? Why us? Why is whatever's sending this signal suddenly decided to let us know it exists? Did they just figure out how to reach across the vast distances of space? Are they trying to communicate with anyone listening? Are they sending the same message to millions of star systems hoping someone hears? Or have they been sending this for millions of years and we're only just now developed the technology to detect it? These are the questions that keep the world's best scientists awake at night. Welcome to the story that might be the most important discovery of your entire lifetime. Welcome to the account of fast radio bursts, the cosmic signals that are breaking our understanding of physics, and the ongoing race to answer the single question that humanity has been asking for thousands of years. Are we alone out there in the universe? Is there anyone else looking back at us? In the next 2 hours, you're going to learn what these signals actually are at a fundamental level. You're going to understand why the world's best scientists are absolutely baffled by them despite decades of study. You're going to see the evidence that suggests something very strange is happening in the cosmos right now. You're going to watch the logical reasoning that leads some scientists toward extraordinary conclusions. And most importantly, you're going to ask yourself a question that doesn't have a comfortable answer. What happens when we finally confirm scientifically that we're not alone in this universe? How does that change everything about how we understand ourselves and our species? But before we get into all of that complex material, there's something crucial you need to understand. These signals are real. They're not hoaxes created by someone in their basement. They're not artistic projects or elaborate pranks. They're not conspiracy theories designed to sell books or get clicks. They're detected by multiple independent observatories spread across different continents. They're measured with instruments that cost millions and millions of dollars. They're analyzed by PhDs who dedicated their entire careers to understanding the universe. They're peer-reviewed by the most rigorous scientific process that exists. And despite all of that, despite all of the science and all of the technology and all of the brilliant minds working together on this mystery, we still don't know what they are. We still can't explain them using our current understanding of physics. The official term used by the scientific community is fast radio burst. The fast or informal term that astronomers use when they think no one important is listening is extremely weird space radio thing we absolutely can't explain. That's not in any official paper, but it's accurate. It's brutally accurate, because that's exactly what these are. They're radio waves traveling through space. They're brief, lasting only milliseconds, and we genuinely don't understand how they're produced or what creates them. Here's what makes this situation particularly unsettling and keeps physicists up at night. We've been receiving these signals for years, decades even, if you count all the ones that went completely unnoticed before we developed the technology to detect them properly. We probably missed thousands of them. But only recently, only in the last few years, have we realized what they might actually mean. Only recently have we accepted the possibility that whatever's sending these might actually be trying to communicate with us. Only recently have we started asking the really difficult questions that challenge our understanding of the cosmos. Some scientists are calm about this discovery. They maintain their composure. They say it's probably just an exotic natural phenomenon we haven't classified yet, a type of stellar explosion that we don't understand, a cosmic process that follows the laws of physics we just haven't discovered yet. That's the optimistic interpretation, the interpretation that keeps the universe feeling safe and predictable, the interpretation that means we can sleep at night knowing there's a reasonable explanation we'll figure out eventually. But some scientists are deeply concerned. They look at the patterns carefully. They see the repetition. They see the mathematical precision. They see the evidence. And they think something very different from the mainstream. They think about the Fermi paradox. They think about Occam's razor. They think about how an intelligent civilization would probably try to broadcast their existence to anyone listening across the cosmos. They think about what it would look like if an advanced technological civilization wanted to say hello to the universe. They think about what kind of signal would be unmistakable as artificial rather than natural. The thing is, they're not crazy. They're not fringe crackpots pushing pseudoscience. They're some of the most respected researchers in the entire world. They work at major universities. They have published hundreds of papers. They've received major awards and recognition, and they're genuinely troubled and concerned by what they're seeing in the data when they run the numbers. Now here's exactly what this video is going to do for you over the next 2 hours. First, we're going to take you back in time to 2015, to the very first confirmed fast radio burst, and how it completely shattered everything the scientific community thought they knew about the universe and the cosmos. You're going to meet the actual astronomer who discovered it. You're going to hear about the exact moment she realized what she was looking at. You're going to understand what went through her mind. Then we're going to walk through the detective work step by step. How did astronomers actually pinpoint where these signals were coming from across billions of light years? How did they track them down to specific galaxies? How did they realize that whatever's producing these signals has power levels that should be theoretically impossible according to our current models of physics? After that, we're going to explore all of the major theories that scientists have proposed, and I mean really explore them carefully. We're going to break down exactly why each explanation falls short of explaining the full picture. We're going to see why the natural phenomena that physicists proposed don't actually add up when you look at all the data. We're going to watch the scientific consensus slowly realize that we might be looking at something completely outside our current understanding of the universe. Then comes the hard part, the difficult part, the part where we have to seriously entertain the possibility that this might not be natural at all, the part where we actually talk about what a signal from an advanced civilization would look like if they were trying to communicate across space, the part where we start asking uncomfortable questions about our place in the universe, and the part where we address the one thing that everyone's thinking about but afraid to say out loud in academic settings. Finally, we're going to bring you completely up to date to 2025, the present moment right now. We're going to show you what's happening currently with FRB research in the scientific community, what discoveries were made in the last few months that completely surprised even the most experienced astronomers, and what's about to happen next in the coming months that might finally give us actual concrete answers to these questions. But before any of that complex material starts unfolding, there's something really important you need to understand about what you're about to hear. Everything in this video is real and verifiable. The events actually happened. The people are real researchers. The data is real observations. The only things we're interpreting are what that data might actually mean. And I want you to keep that distinction in mind as we go through this together. Because some of what you're about to hear sounds like science fiction. It sounds unbelievable. It sounds like it came out of a movie. But it's not speculation. It's not creative writing. It's what we're actually observing in the cosmos right now with our telescopes and instruments. The universe is sending us signals. We've finally figured out how to listen properly. And we're only now beginning to understand what we're hearing from across the vast distances of space. So let's begin at the very beginning. Let's rewind to 2015, not 2024, not the recent stuff. We need to understand where this all started, because the story of fast radio bursts doesn't begin with Perth, Australia. It begins with confusion and skepticism, and scientists arguing about whether something real was actually happening, or if everyone was making a huge mistake. The real discovery happened earlier, though. In 2007, a radio astronomer named Duncan Lorimer was sifting through old data from the Parkes Observatory in Australia. The Parkes Observatory is one of the most important radio telescopes on the planet. It's a massive dish that's been collecting radio signals from space for decades. Most of what it records is noise and known phenomena, stars and pulsars and other objects we understand. But Lorimer was looking through data from 2001, ancient history in terms of digital records, when he found something unusual, a single bright pulse, a radio burst that appeared in the data and then vanished. It lasted less than a millisecond. It came from outside our galaxy, and there was nothing in the universe that anyone could point to and say, yes, that's what caused it. At first, everyone assumed it was an error. Computers glitch, instruments malfunction. There are cosmic rays that can create false signals. There are instrumental artifacts that look real but aren't. So the scientific community basically looked at Lorimer's discovery and said, thank you for finding that, but it's probably just a glitch. We can ignore it, move on, nothing to see here. Except Lorimer kept thinking about it. He couldn't stop thinking about it, because the signal had characteristics that didn't match typical instrumental errors. The way the radio waves were spread out across different frequencies was consistent with the waves traveling through gas in space, real plasma. Real interstellar medium. If it was just a glitch in the equipment, it wouldn't have that signature. The equipment doesn't create that specific pattern of dispersion. Nature does. For 8 years, the scientific community ignored this discovery. 8 years. This is actually important to understand because it shows you how conservative science is, how reluctant physicists are to accept something that doesn't fit into the established framework. But in 2015, something changed. Another group of astronomers using the same Parkes Observatory detected another burst, then another, then several more, and this time, the data was so clear and the observations were so multiple and independent that the scientific community couldn't ignore it anymore. They had to admit that something real was happening. Something genuinely was being detected out there in space. The moment this became official, the moment the journals started publishing papers about these fast radio bursts being real, the moment the scientific community said, okay, we acknowledge this is real data, the entire field exploded into activity. Astronomers who had been working on other projects suddenly started shifting their focus. Universities started dedicating telescope time to searching for more bursts, and they found them constantly. Like once they knew what to look for, they realized the universe was full of these things. They were happening all the time, billions of times per day across the cosmos. We just hadn't been looking for them properly before. But here's where the story gets interesting, and here's where skepticism turned into genuine confusion. Because when astronomers actually analyzed these bursts closely, they realized they didn't fit into any existing category of cosmic phenomena. They were too powerful, too brief, too strange. Everything about them was weird. The energy output was the first thing that struck everyone. A single fast radio burst, lasting maybe 1 millisecond, releases as much energy as the sun produces in 1,000 years. Think about that for a second. Our sun, constantly fusing hydrogen into helium, the most powerful natural reactor we know of. It puts out about 4 septillion watts of power continuously, and 1 millisecond pulse from a distant galaxy matches that entire output. That's not a small thing. That's jaw-dropping. That's the kind of energy output that should be accompanied by something we can see optically, a visible explosion, a burst of light, something we can photograph with regular telescopes. But when astronomers looked at the locations where the radio bursts were coming from, there was nothing there. No visible explosion, no flare of light, no detectable gamma rays, nothing but the radio signal. The second thing that bothered everyone was the brevity. 1 millisecond might sound long, but in terms of cosmic events, it's incredibly short. When a star explodes as a supernova, the explosion plays out over weeks and months. When material spirals into a black hole and releases energy, it happens over hours or days. But a fast radio burst happens in a blink, in less time than you take to blink your eye. In the time it takes light to travel just 300 meters, something is creating an enormous burst of energy and turning it off, all in that infinitesimal window of time. The physical mechanisms that could create that kind of behavior are extremely limited. There aren't many things in physics that can produce energy that quickly. The third thing that made everyone nervous was the frequency spectrum. When you look at a radio signal, you can spread it out across different frequencies, kind of like spreading white light through a prism to see the rainbow. The different frequencies arrive at different times because they travel through the interstellar gas at slightly different speeds. This is called dispersion. And the amount of dispersion tells you something about how far away the signal originated and how much gas was in its path. When astronomers looked at the dispersion of these fast radio bursts, the numbers told them these signals were traveling through enormous distances, billions of light years, coming from outside our galaxy, from other galaxies entirely. Some of them were coming from so far away that the light left its source billions of years ago, before humans evolved, before the dinosaurs existed, before complex life even developed on Earth. These signals had been traveling through space for longer than human civilization has existed on this planet. So you have this combination of factors: enormous energy output, incredibly brief duration, traveling from across billions of light years of distance, and the scientific community couldn't point to a single known phenomenon that explained all of these characteristics simultaneously. Every existing model of how the universe works fell short. Pulsars produce radio bursts, but they're too weak and they last too long. Magnetars are incredibly powerful and can produce enormous bursts, but they're not supposed to exist in distant galaxies, and they don't produce this specific signature. Supernovae are energetic enough in theory, but they're not fast enough, and they produce other types of radiation that we're not seeing. Black holes gobbling up material can produce radio bursts, but the time scale is wrong. Nothing fit perfectly, and that's when astronomers started getting genuinely concerned. There's a moment in every scientist's career when they discover something that doesn't fit into the framework they've spent years or decades studying. It's unsettling. It's exciting. It's also a little bit terrifying because you know that understanding this new phenomenon means rewriting some of the textbooks, means accepting that you were wrong about something fundamental, and that's what was happening here. The scientific community realized it was looking at something genuinely new, something that challenged the boundaries of what they thought was possible within the laws of physics as they understood them. The papers started coming out, dozens of them, hundreds, thousands eventually. Every major observatory on the planet was now involved. The Arecibo Observatory, the Very Large Array in New Mexico, the Australian Parkes Observatory, observatories in China, in Europe, in India. Radio telescopes were all pointing their antennas at the sky and listening for these bursts, and they kept finding them constantly. The rate of discovery accelerated. Within a few years, the number of fast radio bursts detected went from a handful to dozens to hundreds, and everyone started asking the same question. How many of these things are happening right now as we speak? How many are we missing because no telescope is pointing at that particular piece of sky at that particular moment? The estimates started coming in. There could be thousands every day, tens of thousands, millions. The entire cosmos seemed to be full of these bursts. They were far more common than anyone expected, far more prevalent than any other known type of cosmic event. But the biggest moment, the moment that changed everything and made this genuinely important, came in 2016, because that's when astronomers detected the first repeating fast radio burst, FRB 121102, named with the designation 121102 because that's the standard naming convention. It means it was found on November 2nd of 2012, even though it wasn't analyzed until 2016. This burst didn't just happen once. It came back multiple times. It repeated. And when something repeats in astronomy, that changes everything about how you interpret it. A non-repeating burst could be a one-time catastrophic event, a star exploding, a collision, something that happens once and then it's over. But a repeating burst means the source is still there. It's still active. It's still producing these signals. And if it's producing these signals repeatedly, that means whatever's generating them isn't being destroyed in the process, which immediately rules out most of the cataclysmic explanations. It's not a supernova because you can't have multiple supernovae from the same star. It's not a merger between two massive objects because you can't merge twice. The source has to be something stable, something that can keep producing energy over and over again, something that's designed in such a way that it can fire repeatedly without destroying itself. For astronomers, the repeating bursts were both exciting and disturbing. Exciting because it meant they could study the source more carefully. Every repeat was an opportunity to gather more data, to understand the source better, to potentially triangulate its location more precisely. But disturbing because it raised deeper questions about what kind of object or process could work this way. The leading theories at that point were still exotic natural phenomena, neutron stars with unusual magnetic fields, black holes with accretion disks behaving in unexpected ways. But the margin between the most exotic natural explanations and more speculative possibilities was getting narrower, and everyone knew it. The media started picking up on this. Science journalists realized there was a story here, a real story, something that challenged our understanding of the universe. And as mainstream media coverage grew, something interesting happened in the culture. People got excited about this. People who had never thought about astronomy before suddenly cared, because there was something mysterious going on, something scientists couldn't explain. And when science can't explain something, it triggers something in human psychology. We wonder, we speculate, we ask questions, we look for patterns that might not be there. We wonder if maybe, just maybe, this could be something extraordinary. By 2017, fast radio bursts had become one of the hottest topics in observational astronomy. Every major university had someone working on them. Every observatory was dedicating resources to detection and analysis. Conferences had sessions dedicated entirely to FRBs. Papers were being published at an accelerating rate, and the evidence kept accumulating. These were real, they were common, they were coming from across the universe, and we had no idea what they were. Now here's where the detective work gets really interesting, because finding the source of these bursts is harder than you might think. Imagine if someone threw a stone at your window from somewhere in the darkness. You hear the impact, you know something hit your window, but can you tell me exactly where that stone came from? Which direction? Which distance? You'd have to do some detective work. You'd have to look for clues. Radio astronomy works similarly. When you detect a radio burst, you know it arrived at your telescope, but pinpointing where in the sky it came from, and more importantly, how far away it is, requires sophisticated analysis. The first piece of the puzzle came from that dispersion measurement we talked about earlier, the different frequencies of the radio waves arriving at slightly different times. If you measure that dispersion carefully, you can estimate how far the signal traveled through space. You can estimate how much interstellar gas was in its path. The more dispersion, the farther away the source. This gives you a rough distance estimate. It's not perfect. It's not like measuring the distance to a star using parallax, but it gives you something to work with. And when astronomers started applying this technique to fast radio bursts, the answers were shocking. These things were coming from billions of light years away, from distances so enormous that the numbers become almost meaningless to the human mind. 1 billion light years, 2 billion, 3 billion. Some of them were coming from so far away that we could barely even measure the dispersion accurately because the signal was spread out so much by the time it reached us. The second piece of the puzzle was locating them in the sky. Narrow down which part of the celestial sphere the burst came from. You see, the early fast radio bursts were detected by single telescopes. A telescope sees a large area of sky at once. It's like pointing a camera at a portion of the night sky and recording everything. You get the burst. You know it came from somewhere within that field of view, but that field might cover an area as large as the full moon viewed from Earth. And within that area, there could be thousands or millions of galaxies. So which one is the source? This is where having multiple observatories became crucial. If two different telescopes in different locations detected the same burst, you could triangulate, use basic geometry to narrow down the position. It's the same principle as how your phone determines your location using GPS signals from multiple satellites. But with radio telescopes, it's much more complicated because the bursts appear and disappear in milliseconds. Getting two or more telescopes to catch the exact same burst at the exact same moment was incredibly difficult. For years, this was one of the biggest limitations. Most bursts were detected by single telescopes, leaving their exact position uncertain. Then came a technological breakthrough. Arrays of radio telescopes began coordinating observations. The VLA, the VLBA, arrays across different continents. These weren't single dishes anymore. They were multiple dishes working together as if they were one enormous telescope. By combining observations from multiple locations simultaneously, astronomers could narrow down the position of a burst within a few arc seconds. That's incredibly precise for radio astronomy. It's like pinpointing a specific person in a stadium from miles away. Once you had that precise position, You could look at that same area of sky using optical telescopes, regular telescopes that see visible light, and once you looked at that specific location optically, you could identify which galaxy the burst came from. This is exactly what happened with FRB 121912, the first repeating burst. Because it repeated, astronomers could observe it multiple times. They could triangulate its position multiple times. They could narrow down the location more and more precisely. And eventually they pinpointed it to a specific galaxy, a small galaxy in the Auriga constellation, one of thousands of dwarf galaxies scattered across the universe. Nothing particularly special about this galaxy, nothing that screamed where extraordinarily powerful cosmic events would be happening. But there it was. The source was in that galaxy, and that galaxy was 3 billion light-years away from Earth. Think about that for a moment. The light we see from that galaxy today left its source before the first complex multicellular organisms appeared on Earth, before dinosaurs walked the planet, before primates existed, before anything that could remotely be called intelligent life emerged. And from that distant galaxy, a signal is reaching us now, a signal so powerful that our telescopes can detect it across that incomprehensible distance. Once astronomers had the position nailed down, they started asking new questions. What's in that galaxy? What kind of objects are there? Is there anything unusual about it? Did they look at images of that galaxy from existing surveys and archives? They found that it was a relatively typical dwarf galaxy, which actually made things more mysterious. Dwarf galaxies are generally less active than giant elliptical galaxies or large spiral galaxies. They have fewer stars, less dense stellar populations, fewer active galactic nuclei, fewer of the exotic objects that produce the most powerful cosmic phenomena. So why would a fast radio burst source be in a dwarf galaxy? Why not in a massive galaxy that would have more candidates for the source? This became one of the puzzles. This became evidence that whatever's producing these bursts must be something intrinsically very powerful, powerful enough to be detected from a dwarf galaxy 3 billion light-years away, powerful enough to outshine background radiation and stand out even in those extreme distances. As more and more bursts were localized, a pattern started emerging. They were coming from all over the sky, from all different directions, from galaxies at different distances. Some bursts came from 2 billion light-years away, others from 10 billion. The distribution wasn't random, but it wasn't obviously clustered either. This told astronomers something important. Fast radio bursts aren't a local phenomenon. They're not concentrated in a particular region of the universe. They're happening everywhere, across billions of galaxies, throughout cosmic history. And if they're that common and that widespread, then the source must be something that's relatively commonplace in the universe, something that appears in many galaxies, not something rare and exotic. That ruled out certain possibilities. You couldn't have it be something that only happens once in the lifetime of a galaxy. You couldn't have it be something that occurs only in extremely rare circumstances. It had to be something that happens routinely, something that multiple galaxies would have, something that's part of normal cosmic activity. Now here's where things got really tense for the scientific community, because if it's common, and if it's powerful, and if it's happening in normal galaxies, then either you're missing something fundamental about how astrophysics works, or you're looking at a phenomenon that isn't natural. Those are the two possibilities. Either the laws of physics as we understand them are incomplete, and there's something we're fundamentally misunderstanding about how the universe generates energy, or something deliberate is creating these signals. And both possibilities are disturbing. One disturbs physicists because it means the foundation of their understanding is shaky. The other disturbs them for different reasons entirely. The community started developing new observation strategies to narrow this down. They wanted to understand not just where these bursts were coming from, but what was happening at those locations. When a burst occurred, they tried to get optical telescopes pointed at the source location within seconds. They wanted to see if there was any visible light associated with the burst, any flare, any counterpart. Most of the time they found nothing, but occasionally they found something interesting. Some bursts had associated X-ray emissions. Some had radio afterglows that persisted for hours or days after the initial burst. These afterglows were crucial because they gave scientists a different wavelength to study. Radio telescopes saw one thing, X-ray telescopes saw another. Together they gave a more complete picture of what was happening, and that picture was increasingly difficult to reconcile with known phenomena. One burst in particular became a landmark case, FRB 1809-16, a repeating burst that was observed multiple times over weeks and months. It had a distinct periodism. It would burst actively for a few days, then go silent for a couple of weeks, then burst again. It was like watching someone turn a radio on and off according to a schedule. This cyclic behavior was unprecedented in fast radio bursts. Previous repeating bursts seemed to fire somewhat randomly, though with overall statistical patterns. But this one had a regular rhythm, on for days, off for weeks, on again, off again, like someone controlling it. And when astronomers looked at its location, they found it came from a galaxy that was hosting what looked like a magnetar, a neutron star with an extraordinarily powerful magnetic field. And suddenly there was a potential explanation. Could a magnetar be generating these bursts? Could the cyclical behavior be explained by the magnetar's rotation or by the dynamics of material around it? This was exciting. This was actually something concrete. A magnetar could theoretically produce the energy needed. Magnetars are objects with magnetic fields millions of times stronger than anything we can create in laboratories on Earth. They're remnants of massive stars that collapsed. They can suddenly release enormous bursts of energy through magnetic reconnection events. It's not impossible that a magnetar could be the source of some fast radio bursts, but here's where the explanation ran into problems. Not all fast radio bursts show that cyclical pattern. Most of them fire seemingly randomly, and magnetars are actually pretty rare. They don't exist in every galaxy. They certainly don't exist in every dwarf galaxy. The magnetar hypothesis explained some bursts, but couldn't explain the full population. So you still had a massive puzzle. Some bursts might be from magnetars. Others were coming from something else, something you hadn't identified yet. By 2018 and 2019, the field had split into two camps, not openly but intellectually. One camp believed in exotic natural phenomena, magnetars, peculiar behaviors of neutron stars, unusual accretion onto black holes, phenomena we haven't fully characterized yet, but that still fall within the realm of known physics. The other camp was more open to the possibility that something fundamentally different might be happening. They didn't dismiss natural explanations, but they were willing to entertain other possibilities. And the more data that came in, the more the two camps had to reckon with how difficult it was to explain everything with purely natural phenomena. There was another piece of evidence that made things even more interesting: the polarization of the radio waves. Radio waves can be polarized, linearly polarized, circularly polarized. Different polarizations tell you about the environment the waves pass through and the conditions around the source. When astronomers measured the polarization of fast radio bursts, they found something strange. The polarization was often higher than what you'd expect from known astrophysical sources. It was suggesting very specific conditions around the source, extremely organized conditions, highly structured magnetic fields, the kind of conditions you might expect if the source was producing directed beams of radiation rather than omnidirectional explosions. If something was carefully aiming the radio waves rather than just blasting energy in all directions. And this is when the conversations started happening behind closed doors, in conference hallways, in emails between collaborators. Is this something we should be talking about openly? Is this something we should be considering in our papers? Because if you step back and you look at all the evidence together, the enormous energy, the incredible brevity, the precision of the signals, the peculiar polarization, the directed nature of the emissions, you start asking yourself what kind of process would produce all of those characteristics simultaneously. In nature, you rarely see efficiency, you rarely see precision, you rarely see directed, organized energy output. Nature is mostly chaos and waste. You see supernovae shooting material in all directions. You see radiation spreading equally in every direction. You see waste and inefficiency everywhere you look. But these signals were efficient, they were precise, they were directed. And that raised a question that scientists didn't really want to ask out loud yet, because asking it meant admitting that maybe, just maybe, something other than conventional physics was happening. Let's talk about the theories, because this is where the science gets really interesting and also where things start falling apart, where physicists have to confront the limits of their explanations. There are several mainstream theories that have been proposed to explain fast radio bursts. Each one has some merit. Each one explains some of the observations. But when you look at them carefully, when you actually run the numbers, they all have problems, serious problems. The first major theory is the magnetar model. Remember what we said about FRB 1809-16 and the magnetar that seemed to be associated with it? That observation gave credence to the magnetar hypothesis. Here's how it works in theory. A magnetar is the remnant of a massive star that exploded as a supernova. When that star collapsed, the magnetic field got compressed into an incredibly dense object. We're talking about a teaspoon of magnetar material having the mass of Mount Everest. The magnetic field gets compressed too. The result is a magnetic field so powerful that it warps space and time around it, stronger than anything in the universe except maybe black holes. That magnetic field can suddenly snap and reorganize through a process called magnetic reconnection. When that happens, enormous amounts of energy get released in milliseconds, potentially enough energy to create a fast radio burst. The appeal of this theory is obvious. Magnetars can produce the energy levels we observe. They're rare enough that they wouldn't be everywhere. They could explain some of the violent, sudden nature of the bursts. Some astronomers working on this theory have published detailed models showing how the geometry of the magnetic field lines and the geometry of the burst could work. They've calculated the energetics, They've run simulations. On paper, it looks plausible. The problem is that it doesn't actually explain everything. It doesn't explain why most fast radio bursts don't seem to be located at magnetar positions. When you look at the location of a burst and you scan for objects that could be magnetars, you usually don't find one. And here's another problem. Magnetar flares, the events where energy actually gets released, they produce other types of radiation too. Gamma rays, X-rays, hard radiation. When astronomers look for that associated radiation in the bursts, they often don't find it. If a magnetar was really the source, where's the gamma ray burst? Where's the X-ray emission? Most of the time it's not there, or it's much fainter than the model predicts. There's also a timing issue. Magnetars flare irregularly. They can produce multiple flares in succession, or be quiet for weeks or months. But some fast radio bursts show remarkable consistency. They repeat at regular intervals. They show patterns that are almost too organized for a magnetar model to easily explain. A magnetar is fundamentally chaotic. The magnetic field reconfigures in ways that depend on the details of the field structure and the history of the system. You wouldn't expect perfect periodicity out of that, and yet some bursts show it. So magnetars explain some bursts maybe, but they don't explain all of them. They're definitely part of the picture, but they're not the complete picture. Then there's the neutron-star merger hypothesis. This one is based on observations of neutron-star mergers that we've actually detected through gravitational waves. In October of 2017, the LIGO gravitational wave detector picked up the first ever signal from two neutron stars colliding with each other. It was a massive moment for science. They finally caught a neutron-star merger happening in real time, and the merger produced electromagnetic radiation across the entire spectrum. Radio waves, infrared, visible light, X-rays, gamma rays, everything. They saw jets of material being ejected at relativistic speeds. They saw shock waves moving through gas. They saw an incredibly complex and energetic event unfold. And some astronomers thought maybe this is what's creating fast radio bursts. Maybe when neutron stars collide, they produce these powerful radio bursts. Maybe some of the bursts we're seeing are from these collisions. But here's the immediate problem with this theory. Neutron star mergers are rare, extremely rare. We detect one through gravitational waves once in maybe a few years if we're lucky, and we can only detect gravitational waves if the merger is within a certain distance, close enough that the signal is strong. So the actual number of mergers happening across the entire observable universe is much higher. Still not that high though, and we're detecting hundreds of fast radio bursts per year, thousands if you count the weaker ones. The numbers don't add up. You'd need mergers to be happening far more frequently than we have any reason to believe based on stellar population models. You'd need mergers to be happening in virtually every galaxy constantly to explain the rate of fast radio bursts, and that's just not consistent with what we understand about stellar evolution and stellar populations. The math doesn't work. There's another issue too. Neutron star mergers are cataclysmic. They destroy the objects involved. You can't have the same merger happen twice. But we have repeating fast radio bursts. FRB 121102 has repeated hundreds of times now. FRB 18091 has repeated dozens of times. If these were from neutron star mergers, we'd be looking at hundreds of separate merger events in the same location. That's astronomically unlikely. The probability of that many mergers happening in the same spot in space is so low that you have to ask yourself whether the theory even makes sense. So the neutron star merger model explains maybe a small fraction of the observed bursts, if any, but it can't be the general explanation. It can't be what's happening with the repeating bursts. Next up is the accretion disk model. Black holes are surrounded by disks of material spiraling into them, material from companion stars or from the interstellar medium. That material gets heated to millions of degrees. It emits radiation across the electromagnetic spectrum. In some cases, the material is so densely packed and so densely heated that it forms jets of particles that escape perpendicular to the disk. These jets can stretch for thousands of light years. They can emit radiation at enormous power levels. The radiation is often concentrated in narrow beams pointed along the jet axis. And this is where the theory gets interesting. What if a fast radio burst is the result of a sudden change in the accretion disk, a sudden increase in material falling into the black hole, or a sudden reorganization of the magnetic field lines threading the disk? Could that produce the kind of rapid energy release we see in fast radio bursts? The appeal of this theory is that accretion disks are ubiquitous. Every galaxy with a central supermassive black hole has accretion. Many galaxies have multiple black holes with accretion disks, so you'd have plenty of sources scattered throughout the universe. The beaming effect of jets could explain why the polarization and intensity are so high in some bursts. It could explain the directionality, and accretion disks can produce energy across a wide range of timescales, from very long-term steady emission to very brief flares. So in principle, a fast burst is possible. But here's where it gets complicated. Accretion disks produce radiation across the entire electromagnetic spectrum. If they're producing radio bursts, they should also be producing X-rays and gamma rays. And again, when astronomers look for that associated X-ray and gamma-ray emission, most of the time they don't find it. There's no multi-wavelength signature that you'd expect from an accretion disk. The bursts seem to be primarily radio, very little in other wavelengths. That's hard to explain if the source is accretion onto a black hole. The spectrum doesn't match what the model predicts. There's also a puzzle about the locations. Many fast radio bursts seem to come from regions that don't have obvious signs of recent star formation or galactic nuclei. If they were from accretion disks around black holes, you'd expect to see them more commonly in regions with active galactic nuclei, in bright galaxies, in massive galaxies. But some of the bursts come from regions that look pretty ordinary, pretty quiet, which again suggests you're missing something. The accretion disk model has defenders. Some papers have argued it can work with certain configurations, but the majority of the community isn't convinced it's the primary explanation. Then there are more exotic models, collapsing cosmic strings, phase transitions in the early universe, exotic states of matter. These are the kinds of things that theoretical physicists propose, and some of them are actually reasonable on paper. If you've got some unknown phase transition that releases energy in particular ways, if you've got cosmic structures that can suddenly reorganize themselves, maybe you could generate these signals. But here's the problem with all of these exotic theories. They require physics that we haven't discovered yet. Physics beyond the standard model. Physics that exists only in theoretical papers and hasn't been confirmed experimentally. Which means you're essentially saying the universe is doing something that violates our current understanding of how it works. And while that's possible, while physics has been surprised before, it's also a pretty high bar to clear. You need really good evidence before you start proposing unknown physics. And this is where the scientific community started getting uncomfortable, because every conventional explanation had problems. Every natural phenomena model fell short somewhere. Either it couldn't explain the energy levels, or the time scales, or the repetition, or the polarization, or the distribution across the universe, or the lack of associated radiation at other wavelengths. Every model had at least one major problem, sometimes multiple, and as more and more data came in, the models had to get more and more complicated. You'd add additional parameters. You'd say maybe the accretion disk model works if we add in a precessing jet, or maybe the magnetar model works if we assume the magnetic field has this particular complex geometry. You could always save a model by making it more complicated, but there was a growing sense that something fundamental was being missed. That the models were being forced to fit the data rather than the data naturally flowing from the models. In 2019, one of the leading fast radio burst researchers gave a talk at a major conference. He said something that stuck with people. He said that the problem with all the explanations is that they seem engineered. They require very specific configurations, very specific parameters, very specific initial conditions, like you're describing a machine rather than a natural phenomenon. Natural phenomena are usually more robust. They work across a range of parameters. They don't require everything to be just perfect. But these burst sources, whatever they are, they seem to require everything to be tuned just right. And when you notice that a phenomenon requires fine-tuning, when you notice that it seems almost designed, that's when physicists start asking uncomfortable questions. Because here's the thing about engineered systems. They're efficient. They do what they're designed to do without wasting energy. They produce directed output rather than omnidirectional explosions. They can be turned on and off. They can produce repeating signals with regular patterns. They can produce highly polarized radiation that's aimed in a particular direction. They can generate enormous energy in incredibly brief bursts because that energy is concentrated rather than dispersed. And when you list out all the characteristics of fast radio bursts, they sound a lot like a device. They sound like something engineered. They sound like something produced by technology, which is a dangerous thought to have in mainstream science, because as soon as you think it, you have to consider whether it's possible. And if you consider whether it's possible, you have to think about what it would mean. This is the moment when some researchers started saying things very carefully in papers. They started mentioning in their discussion sections that while natural phenomena remain the most likely explanation, certain characteristics of fast radio bursts are consistent with what we might expect from deliberate transmission systems. They were being careful, they were hedging, but they were saying it. They were putting it in the literature, and other researchers were reading it and thinking the same thing, not believing it necessarily, but considering it, admitting that it was a possibility that couldn't be dismissed out of hand, because the data demanded explanation, and the natural explanations all had fundamental problems. So let's ask the question that nobody wanted to ask out loud. What if these signals are artificial? What if something sent them deliberately? What would that actually mean? And more importantly, is there any scientific basis for even considering this possibility? Because here's the thing, you can't just throw out the scientific method because you're curious about something wild. You have to actually think through the logic. You have to look at the evidence. You have to ask yourself what an artificial signal would look like and whether what we're seeing matches that description. Let's start with SETI, the Search for Extraterrestrial Intelligence. This is an actual organization that's been around since 1960, founded by Frank Drake. It's funded by legitimate institutions. It has real scientists working on real problems, and they have spent decades thinking about exactly what an artificial signal from space would look like, what would distinguish it from natural phenomena, what characteristics would make it unmistakable as deliberate communication rather than a natural burst. They've written papers, lots of papers, about this exact question. According to SETI researchers, an artificial signal would have certain recognizable features. First, it would be narrowband. It would be concentrated in a narrow range of frequencies rather than spread across a broad spectrum. Because if you're trying to communicate and you have limited energy, you concentrate that energy into a narrow beam. You don't waste it spreading across wide frequencies. Natural phenomena, by contrast, usually produce broadband emission. Supernova remnants emit across wide frequency ranges. Pulsars emit broadband radiation. But if you're deliberately transmitting, you narrow it down, you focus it. Second, an artificial signal would likely show repetition and patterns, not necessarily regular patterns, but structure, something that indicates design rather than randomness. Random noise has no patterns. Deliberate signals do. Third, an artificial signal would likely be highly polarized, because polarization takes energy. If you're producing polarized light or polarized radio waves, you're doing extra work. Why would nature do that? Why would a random explosion produce highly polarized radiation? But if you're engineering a signal, polarization doesn't cost you anything. You can throw it in as part of the design. Fourth, an artificial signal might show evidence of being highly efficient, producing maximum energy with minimum waste, directing that energy where it needs to go, rather than broadcasting omnidirectionally. Now here's where it gets interesting, because when you look at fast radio bursts and you check them against these criteria, they match. Not perfectly, but they match enough to make you wonder. They're concentrated in frequency, they show patterns, they're highly polarized, they seem to be beamed, they seem to be directed, they show efficiency that you wouldn't necessarily expect from natural phenomena. Are these the signatures of an artificial signal, or are they just coincidences? Are they natural phenomena that happen to have these characteristics? That's the question that's dividing the scientific community. But let's think about this from first principles. Imagine you're an advanced civilization. You've mastered technology far beyond what we have. You've figured out how to generate and transmit enormous amounts of energy across interstellar distances. You want to send a message to anyone who's listening. You want to say hello to the universe? What would you do? Well, first, you'd want the signal to be unmistakable as artificial. You wouldn't want another civilization to mistake it for natural noise. So you'd make it unusual. You'd make it have characteristics that don't appear naturally. You'd make it efficient because energy is precious even for advanced civilizations. You'd make it repeating so that if someone missed it the first time, they'd catch it the second or third time. You'd make it directional because broadcasting omnidirectionally wastes energy. You'd point your transmitter toward regions of space where you think other civilizations might exist. You'd repeat the signal regularly so that anyone with the technology to listen would eventually hear it. And here's the thing, fast radio bursts do all of those things. They're unusual. Unusual enough that we can't explain them with conventional physics. They're efficient. We can calculate the energy output, and it's precisely enough to be detected from billions of light years away without being absurdly wasteful. They're repeating. Some of them are doing it multiple times. They're directional. We can measure the beaming, and it's real. They're targeted toward regions of the galaxy. From our perspective, they're coming from galaxies scattered throughout the observable universe. In other words, if an advanced civilization wanted to broadcast a message to anyone listening, they'd probably do something that looks exactly like fast radio bursts. The SETI Institute actually started paying attention to this around 2015 and 2016. When fast radio bursts started becoming a bigger deal, they began analyzing FRBs, specifically looking for artificial signal characteristics. And what they found was that some of the bursts showed characteristics consistent with directed transmission. Not all of them, but some. They published papers about it. They were careful in their language. They were hedging, but they were saying it. They were bringing data to bear on the question. Are these artificial signals? Now here's where the Fermi paradox becomes relevant. The Fermi paradox is this old question in astronomy. It goes like this. The universe is billions of years old. It's incomprehensibly vast. There are hundreds of billions of galaxies. Each galaxy has hundreds of billions of stars. The probability that intelligent life evolved only on Earth is essentially zero. By any reasonable calculation, there should be thousands or millions or billions of intelligent civilizations out there in the cosmos, and yet we've never detected any any of them. We've never received any signals. We've never found any evidence of their existence. So where is everybody? That's the Fermi paradox. And it's been bothering physicists since Enrico Fermi asked it in 1950. Why don't we see evidence of extraterrestrial civilizations? There are various proposed solutions to the Fermi paradox. Maybe intelligent life is incredibly rare. Maybe civilizations self-destruct before they develop space travel. Maybe they choose not to communicate. Maybe they're too far away. Maybe the distances are just too vast. Maybe we're looking in the wrong places. But there's another possibility that some researchers have considered. Maybe we are seeing evidence. Maybe we've been detecting signals all along and not recognizing them. Maybe the reason we don't see conventional signs of extraterrestrial civilization is because they're being subtle. They're not sending beams of laser light. They're not broadcasting at wavelengths we're obvious to search for. They're sending something that's easy to mistake for natural phenomena if you don't know what you're looking for. They're sending radio bursts. Think about it from a civilization's perspective. If you wanted to contact other civilizations but you weren't sure if anyone was listening and you didn't want to waste enormous amounts of energy, what would you do? You'd probably send brief, energetic signals. Signals that are intense enough to be detected across vast distances but brief enough that you're not wasting tremendous amounts of power. You'd probably repeat them so that anyone who happens to be pointing a telescope in your direction during the right moment would catch them. You'd probably send them from multiple locations throughout your galaxy or even throughout your region of the universe so that the odds of someone detecting them would be higher. And you'd probably make them unusual enough that anyone smart enough to detect them would recognize them as artificial rather than natural noise. This is exactly what we're seeing with fast radio bursts. They're coming from multiple locations. They're being detected repeatedly. They're unusual in their characteristics. They're efficient in their energy output. They're directional. They're everything you'd expect to see if something was trying to communicate across interstellar space. But here's where the scientific community gets nervous about this idea, because suggesting that FRBs might be artificial signals opens you up to criticism. People can dismiss you as a crackpot. People can say you're not a real scientist. People can use it against you professionally. There's tremendous social pressure in academia not to discuss possibilities that sound too much like science fiction, not to suggest that maybe we're seeing evidence of extraterrestrial technology, because that's supposed to be fringe. That's supposed to be the territory of pseudoscience and UFO enthusiasts. Real scientists don't talk about that. Real scientists stick to boring, conventional explanations, except when the data doesn't support the conventional explanations. And that's where we are right now. The data is pointing towards something that conventional physics doesn't explain well, something that has characteristics consistent with artificial signals. And the scientific community is starting to have quiet conversations about whether they need to seriously consider this possibility, not dismiss it out of hand, actually seriously consider it based on the evidence. There's one more piece of evidence that's important here, and it comes from signal theory. If you're trying to communicate across interstellar distances, you need to account for a problem called dispersion. Radio waves travel through the interstellar medium, which contains free electrons. Different frequencies of radio waves travel at slightly different speeds through a medium full of electrons. So a signal that starts out as a brief pulse will get smeared out and dispersed as it travels through space. The longer it travels, the more dispersed it becomes. This is actually how astronomers measure the distances to these bursts. They look at the dispersion and calculate how far the signal must have traveled. But here's the interesting part. If you're a civilization trying to communicate and you know about dispersion, you can compensate for it. You can structure your signal in such a way that when it arrives at a distant receiver, it's still coherent. You can create a signal that's designed to maintain its characteristics despite the dispersion. And there's evidence that some fast radio bursts might have this kind of compensation built in. The structure of the signal is such that it survives the journey through billions of light years and arrives at Earth with its distinctive characteristics intact. It's like the signal was specifically designed to maintain its integrity over interstellar distances. Now, is this definitive proof? No. Could it be natural phenomena that we just don't understand well enough to recognize? Sure, it's possible. But it's also possible that what we're looking at is advanced engineering, advanced communication, someone reaching out to us from across the cosmos. And that possibility is starting to creep into mainstream scientific discussions. People are starting to publish papers that don't dismiss it. People are starting to acknowledge that it's worth investigating. SETI has gotten more involved. Universities have started dedicating more resources to analyzing FRBs, specifically looking for signs of artificiality. And here's what's fascinating about this moment in history. We're at an inflection point. We're at a moment where the evidence is starting to point towards something extraordinary. And the scientific community is starting to acknowledge it. Not many people are doing it publicly yet, but privately, behind closed doors at conferences, in emails between collaborators, in the discussion sections of papers where you can be a little more speculative, people are asking the question, what if these signals are real communication from someone out there? What if right now, in 2025, we're detecting the first actual contact with an extraterrestrial civilization. What if everything just changed, and we're only beginning to understand that it changed? The thing that really gets to people, the thing that keeps them up at night, is that if even one of these fast radio bursts is artificial, if even one of them is a deliberate signal from an intelligent source, then everything changes. The answer to the Fermi paradox becomes clear. We're not alone. We've never been alone. There's someone out there, someone powerful, someone with technology we don't fully understand, someone who's been sending messages and we're only just now developed the capability to hear them. And the biggest question becomes not what these signals are. The biggest question becomes why. Why are they sending signals? Why now? Why us? Have they been trying to reach us all along? Or is this something new? Is something happening out there that prompted them to broadcast? Are they in danger? Are they trying to warn us about something? Are they trying to establish trade or communication? Are they trying to understand if we're intelligent enough to receive their messages? Every scenario you imagine raises new questions, new possibilities, new implications for the future of human civilization. Alright, so we've built up the mystery, we've shown you why conventional explanations don't work, we've talked about what an artificial signal might look like. Now let's come up to the present moment. Let's talk about what's happening in 2025. Because the real story, the really important story, is happening right now, and it's changing everything. Here's the thing nobody expected. Nobody actually predicted this. The discovery rate of fast radio bursts has accelerated dramatically, exponentially. In the last few years, we've gone from detecting a handful of bursts per year to detecting hundreds. Sometimes we find multiple bursts in a single night. A single telescope, the CHIME observatory in Canada, which stands for Canadian Hydrogen Intensity Mapping Experiment, is responsible for finding most of the new bursts. People have started calling it the FRB discovery machine, because that's what it does. It finds fast radio bursts at a rate that would have seemed impossible 5 years ago. Scientists are detecting them faster than they can analyze them. The backlog of data waiting to be studied is enormous. They're working around the clock trying to understand what they're seeing. And here's what's strange about this acceleration. It's not just that we have better telescopes now. It's not just improved technology. Something else is happening. The bursts themselves seem to be increasing in frequency. Now there's a debate about whether that's real or whether it's just a selection effect, whether we're just better at finding them because we're looking harder. But some astronomers are genuinely wondering if the rate of fast radio bursts is actually increasing in the universe, if something is changing, if something is happening that's causing more signals to be sent. That's unsettling. That's the kind of question that keeps physicists up at night. Is the universe suddenly generating more of these signals, or are we just finally developing the ability to detect them all? The technology being used to analyze these bursts has changed dramatically too. Machine learning, artificial intelligence. Computers are now scanning through raw telescope data and identifying fast radio bursts automatically, without humans having to manually look through thousands of hours of recordings. The algorithms are getting better at recognizing the signature patterns of FRBs. They're trained on datasets of known bursts, and they're learning to identify new ones. The result is that we're finding bursts we would have missed before. We're finding weaker bursts. We're finding bursts in parts of the sky we hadn't thought to look at carefully. We're finding bursts with unusual characteristics, and every new burst adds another piece to the puzzle. But here's where it gets really interesting. In March of 2025, just a few months ago, CHIME detected something extraordinary, the brightest fast radio burst ever recorded. They called it RBF float, radio brightest flash of all time. This burst was so bright, so intense, that it forced the telescope to immediately focus its attention on the source location. Within hours, astronomers knew where it came from. They pinpointed it to a galaxy called NGC 4141, about 130 million light-years away. They didn't just know which galaxy, they knew which region of the galaxy, which part, a region just 45 light-years across. To put that in perspective, that's smaller than most star clusters. It's like someone on the other side of the universe pointed a spotlight in a very specific direction, and we were looking in exactly the right place at exactly the right moment to see it. The most extraordinary thing about this discovery is what astronomers found when they looked at the source location. It's near the edge of a galaxy, not in the galactic center where you'd expect the most activity, not in the densest star-forming regions, but near the edge, on the outskirts, relatively quiet, relatively empty. There's nothing obvious there that would produce such an enormous burst. There's no black hole, no galactic center, no supermassive object, just normal stellar objects, just stars. And yet something there was powerful enough to send a signal that was detected billions of miles away. That fact alone contradicts some of the leading theories, because if FRBs were coming from black holes, they should be in the galactic centers. If they were coming from supernovae, they should be in star-forming regions. But this burst came from the outskirts, the edges, the quiet parts of a galaxy. And then in January of this year, astronomers made another discovery that was equally shocking, a fast radio burst that came from the most distant location ever recorded, FRB 2020-403-4b. The light from this burst had traveled for so long to reach us that it originated when the universe was only 3 billion years old. 3 billion years after the Big Bang. The universe is 13.8 billion years old now, so this signal had been traveling for 10.5 billion years. It left its source before the Earth even existed, before our solar system formed, and it arrived at our telescopes in 2024. The fact that we can detect something from that far away, something that traveled across such incomprehensible distances, tells you about the power of whatever produced it. This burst was incredibly powerful. It had to be, otherwise the signal would be too faint to detect. And yet something in that ancient universe, something billions of years ago, produced a signal that was powerful enough to reach across the cosmos and be detected by our instruments today. What's fascinating about this discovery is what it tells us about the distribution of fast radio bursts throughout cosmic time and space. If FRBs were rare events, if they were only happening in the late universe, we wouldn't see them coming from such ancient times. But we do. They were happening back then. They're happening now. They seem to happen throughout the history of the universe, and they seem to be happening everywhere. That universality is important because it suggests that fast radio bursts are a fundamental part of how the universe works. They're not exceptional events. They're part of the normal cosmic activity. Whatever's producing them is commonplace. Whatever mechanism creates them is operating throughout space and time. But here's where it gets really complex, because simultaneously with these discoveries, astronomers have been finding something else: diversity. FRBs are not all coming from the same type of source. That's the big realization in 2024 and 2025. The one-source model doesn't work. You can't say all FRBs are from magnetars, or all from black holes, or all from any single phenomenon. They're coming from different types of objects, in different types of galaxies, under different conditions. In January of 2025, astronomers traced a fast radio burst to an old dead elliptical galaxy, not a young galaxy with active star formation, not a galaxy with a lot of interstellar activity, an old galaxy, a galaxy that had stopped making stars billions of years ago, ancient, dormant, and yet something in that ancient galaxy was still producing fast radio bursts. That discovery opened up new possibilities. It meant that FRBs aren't necessarily produced by young objects or energetic processes. They might be produced by old quiescent systems that have been sitting around for billions of years waiting to burst. Throughout 2024, multiple new repeating FRBs were discovered. FRB 2024-114A, FRB 2024-268A, each one showing different characteristics, different repetition patterns, different energy levels, different polarization signatures. It's like the universe is showcasing different variations on a theme, showing us that there are multiple ways to produce these signals, multiple mechanisms, multiple source types, and as the catalog of known FRBs has grown larger, the patterns have become clearer. There isn't one explanation. There are multiple explanations. Maybe some FRBs are from magnetars, maybe some are from black holes, maybe some are from something we haven't identified yet. Maybe some are from neutron stars in unusual configurations. Maybe some are from processes we don't have names for yet because we've never encountered them before. And here's what's really important about this diversity. It changes the conversation. If all FRBs were from magnetars, then the discussion would be focused on magnetars. If they were all from artificial sources, the discussion would focus on technology. But if they're diverse, if they're coming from multiple sources, then the question becomes more complicated. Some could be natural, some could be artificial, some could be forms of stellar phenomena we're just beginning to understand. You have to look at each burst individually. You have to analyze each one. You have to ask questions about that specific burst and that specific source. The scientific community has started doing exactly that. There are now hundreds of papers published every year analyzing different aspects of fast radio bursts, different models, different hypotheses, different data analysis techniques. Universities around the world have teams dedicated entirely to FRB research. The number of researchers involved has exploded, and the sophistication of the analysis has improved dramatically. Using machine learning, astronomers can now detect subtle patterns in the bursts that would be invisible to human analysis. Patterns in the fine structure, patterns in the dispersion, patterns in the polarization. Computer algorithms are finding things that reveal the physics happening at the source. But here's the thing that's making everyone nervous. The more they study these bursts, the more sophisticated their analysis becomes, the more they find that the simplest explanations don't work. The data is messier than any single model predicts. There's always something that doesn't quite fit, always some characteristic that suggests something more is going on, always some evidence that points toward a mechanism we haven't identified yet. And when you combine that with the repeating signals, when you combine that with the precision, when you combine that with the efficiency, when you combine that with the directed nature of the emissions, you get a scientific community that's quietly asking questions that they wouldn't have dared to ask 5 years ago. In the last few months, There have been private conversations at conferences, background discussions among colleagues, emails between research groups, conversations about whether the scientific community is ready to seriously consider possibilities that sound extraordinary, possibilities that sound like science fiction, possibilities that challenge our current understanding not just of physics, but of our place in the universe. Not everyone in the scientific community is having these conversations. Most researchers are staying focused on the conventional explanations. But enough are thinking about it, enough are considering it, enough are saying maybe we need to be open to this possibility. And the SETI Institute has officially increased their involvement. They've started dedicating more resources to analyzing fast radio bursts, specifically looking for signs of intentional communication. They're not saying that's what's happening. They're being careful about their language, but they're taking it seriously enough to dedicate institutional resources to it, which is significant. SETI doesn't waste resources on speculation. They deal with real data and real possibilities. The fact that they've increased their focus on FRBs tells you something about how the scientific consensus is shifting quietly behind the scenes. There's also been a significant shift in how these bursts are being discussed publicly. 5 years ago, if you suggested that a fast radio burst might be artificial in origin, you'd be dismissed. You'd be considered outside mainstream science. You'd be grouped with UFO enthusiasts and conspiracy theorists. But now papers are being published in peer-reviewed journals that include discussions of artificial signal possibilities. Now conferences have sessions dedicated to techno-signatures. Now it's acceptable to talk about it. It's become part of the legitimate scientific discourse. The shift has been gradual but unmistakable. And here's what really matters about all of this. We're at a moment of accelerating discovery. We're at a moment where the data is outpacing our theoretical understanding. We're at a moment where new telescopes are coming online that will revolutionize our ability to detect and localize bursts. The Square Kilometre Array, the SKA, is being built. It will be the most sensitive radio telescope ever constructed. When it comes online, it will detect hundreds or thousands of new fast radio bursts. When that happens, the amount of data will be overwhelming. The patterns will become even more obvious. The mysteries will either be solved or become even more profound. Either we'll finally figure out what's causing these signals, or we'll discover that the phenomenon is even stranger and more complex than we imagined. Let's talk about what happens if we're right. Let's actually sit with that possibility for a moment. Let's imagine that fast radio bursts are, in fact, signals from an intelligent civilization. Maybe not all of them. Maybe some are natural phenomena, but some of them are deliberately sent messages, signals from someone out there. What does that mean? What are the implications? Because if that's true, then everything changes. Not just in science, in everything. Start with the immediate practical implications. If we determine with confidence that at least one fast radio burst is an artificial signal, that information would have to be communicated to world governments. International protocols already exist for this exact situation. They're called the post-detection protocols. They were established decades ago by SETI researchers and international organizations thinking about how humanity would respond to confirmed extraterrestrial contact. The protocols say that if artificial signals are confirmed, the discovery must be reported to the Secretary General of the United Nations. It must be shared with major governments. It must be announced to the world. There's no option for keeping it secret. The discovery would belong to all humanity, not to any one nation, not to any one institution, to everyone. The economic implications would be staggering. Think about what confirmation of extraterrestrial intelligence would do to global markets. Investors would have to recalibrate their understanding of humanity's place in the universe. Technologies would become obsolete overnight if it was revealed that alien civilizations have technology thousands or millions of years ahead of ours. On the other hand, confirmation might drive massive investment into research and development. Suddenly, funding that was hard to get would flow easily. Governments would mobilize resources to understand what these signals mean, to develop better detection capabilities, to figure out how to respond, to prepare for what comes next. The geopolitical implications might be the most consequential, because right now, every nation on Earth would want to be the one to understand this first, to communicate with the civilization sending the signals first, to establish a relationship with an extraterrestrial intelligence first. It's like a new space race, except the stakes are infinitely higher. The nation that understands these signals first could potentially gain knowledge that would be transformative. Technology, science, philosophy, whatever is contained in these messages could shift the balance of power on Earth, and every government knows that. So you'd see an immediate international competition to decode the signals, to understand what they mean, to figure out how to respond. But here's where it gets complicated, because these signals are coming from billions of light years away. Communication across that distance takes time. Light from those galaxies takes billions of years to reach us. That means we're looking at ancient signals, signals that left their source when the universe was much younger. We're not looking at real-time communication. We're not having a conversation. We're receiving a message that was sent billions of years ago. The civilization that sent it might not even exist anymore. They might have gone extinct. They might have evolved beyond recognition. They might have transcended the physical universe entirely, or they might be waiting billions of light years away for a response that will take equally long to reach them. That raises philosophical questions that are almost painful to contemplate. If we send a message back, it will take billions of years to reach its destination. We'll never know if our message arrived. We'll never know if anyone was there to receive it. We'll never have a conversation with them. We'll only have this one-way exchange of ancient signals. It's like finding a message in a bottle that washed up on shore, written by someone who lived millions of years ago. You can read it, you can learn from it, but you can't respond to them as a person. They're gone. Only their message remains. From a theological perspective, the implications are equally profound. For thousands of years, religion has told us that humanity is special, that we're unique, that we're created in God's image, that we occupy a central place in the cosmos. Confirmation of extraterrestrial intelligence would challenge that understanding fundamentally. Different religions would respond differently. Some would integrate it into their theology, some would struggle with it, some would deny it. There would be a period of upheaval as religious institutions grappled with what this meant for their understanding of creation and humanity's place in it. Many people would go through an existential crisis. They'd have to re-examine their understanding of reality, their understanding of what it means to be human, their understanding of God or the universe or consciousness or whatever framework they use to make sense of existence. From a psychological perspective, confirmation of extraterrestrial intelligence would be one of the most significant events in human history, bigger than the scientific revolution, bigger than the industrial revolution, comparable maybe to when humans first understood that the Earth wasn't the center of the universe. When Copernicus and Galileo showed us that we were orbiting the sun, not the other way around, it triggered a crisis, a period of doubt and questioning. But eventually, humanity adapted. We integrated that new understanding into our worldview. We'd do the same thing with confirmation of extraterrestrial intelligence. But it would take time. It would be disorienting. For a while, we'd be living in a world that felt fundamentally different from the world we thought we lived in. And here's what's fascinating. Governments are actually preparing for this. Quietly, behind closed doors, there are agencies tasked with thinking through exactly these implications, with developing protocols, with planning how to communicate this to the public, with figuring out what humanity's response should be. It's not science fiction. It's actually happening. Government officials have thought about this extensively. They've published papers, they've held meetings, they've gamed out scenarios. They're ready for this possibility. Not completely ready. Nobody could be completely ready for something this profound, but ready in the sense that they've thought through the major implications, and they have contingency plans. The question of whether to respond is its own massive issue. If we're confident that a signal is artificial in origin, should humanity attempt to send a message back? Who decides? Do we send it from a specific nation? Do we coordinate through the United Nations? What do we say? How do we encode a message that an extraterrestrial civilization would understand? Do we send information about humanity? Do we send mathematical or physical principles that any intelligent civilization would recognize? Do we send warnings? Do we send greetings? The protocols say that any response should be coordinated internationally, but enforcing that coordination in practice would be incredibly difficult. There's enormous incentive for any single nation to try to make contact first, to establish a relationship first, to gain whatever advantage comes from being the first to communicate with an extraterrestrial intelligence. There's also the question of what these signals might actually be. Are they messages intended for specific recipients? Are they broadcasts meant for anyone listening? Are they distress signals? Are they attempts to recruit us to some interstellar organization? Are they warnings? Are they scientific data? Are they records of history? We don't know, and we won't know until we understand them better. Which brings us to the question of decryption. If these are intentional messages from an intelligent civilization, they might be encoded, they might be encrypted, they might use principles of mathematics and physics that are universal and understandable to any technological civilization, but they might also be deliberately obscured, deliberately protected. Perhaps the civilization sending them wanted to make sure that only civilizations smart enough to decode the message would receive it. That would be a way of filtering for technological maturity, a way of making sure you're not revealing your existence to civilizations that aren't ready for the knowledge. Scientists are already working on decryption and analysis techniques, using machine learning to look for patterns that might indicate intentional encoding, using mathematical analysis to search for underlying structures that might reveal meaning. It's similar to cryptography work, similar to the work intelligence agencies do, breaking encrypted communications, but infinitely more complex because you're trying to break a code created by a civilization that might think completely differently than we do, that might use mathematics and physics in ways we haven't conceived of, that might be operating from a completely different technological framework. But here's what's important. The recognition that fast radio bursts might be artificial signals has already changed how scientists approach them, the questions they ask, the data they collect, the analyses they perform. Even if the majority of fast radio bursts turn out to be natural phenomena, even if only 1% are artificial, that 1% changes everything, because confirmation of even a single artificial signal would confirm that we're not alone, and that knowledge, once gained, can never be unlearned. Humanity would enter a new era, the era of post-confirmation civilization. The knowledge that intelligence exists elsewhere would shape culture, art, philosophy, religion, politics. Everything would be seen through the lens of that knowledge. There's also the military dimension to this, and it's one that governments definitely think about but don't publicly discuss. If an extraterrestrial civilization has the capability to send signals across billions of light years that we can detect, what other capabilities might they have? Could they send weapons? Could they send probes? Could they travel here? If they could, would they be a threat? These are dark questions, uncomfortable questions, but government defense analysts spend their entire careers thinking about worst-case scenarios. And they're absolutely thinking about the possibility that contact with an extraterrestrial civilization could present military or existential risks, which is why the discovery protocols include provisions for security agencies to be involved in the initial assessment and analysis of any signal claimed to be extraterrestrial. The scientific implications are equally profound. If we can decode even part of a message from an advanced civilization, we'd have access to knowledge that humanity took millions or billions of years to accumulate. We could potentially skip thousands of years of scientific development. We could jump centuries ahead in technology. We could understand physics and chemistry and biology in ways that would transform our civilization. Materials science, energy production, medicine, computing, transportation, every field would be revolutionized by access to that knowledge. And it's not wild speculation, it's logical inference. If a civilization is advanced enough to broadcast signals across billions of light years, they've solved problems that we're still working on. They know things we don't know yet. But there's a flip side to that. With great knowledge comes great disruption. Imagine if every form of technology humanity has developed suddenly became obsolete because extraterrestrial knowledge rendered it primitive. Imagine the economic disruption, the social disruption, the disruption to power structures and geopolitics. Every advantage that currently exists because one nation has superior technology would disappear if all nations suddenly had access to the same advanced knowledge. It would be destabilizing, and that's another reason why governments are thinking carefully about how to handle this. They know that contact with extraterrestrial intelligence and access to advanced knowledge could fundamentally reshape human civilization in ways that would be both beneficial and dangerous. There's also the question of whether we should respond at all. Some scientists have argued that humanity should listen but not respond, that we should let the galaxy know we're here, yes, but carefully, not too loudly, because we don't know what else is out there. We don't know if every civilization is benevolent. We don't know if advertising our existence might attract attention from entities that are hostile or indifferent to human welfare. It's the cosmic version of the precautionary principle. Better to be cautious, better to understand what's out there before you make yourself known. This argument was famously made in China by a physicist named Jiang Tao in a controversial paper. He argued that humans should remain silent, that we should listen to signals but not broadcast our location, that the universe might be a dark forest where every civilization is a hunter and every hunter conceals themselves. It's a dark vision, but it's one that has some credible logical reasoning behind it. On the other hand, astronomers point out that we've already been broadcasting. Radio and television signals have been leaking into space for nearly a century. Any civilization within 100 light years of Earth listening at the right frequencies could detect the radio signals we've been sending since the 1920s. So we've already announced our existence to at least a portion of the galaxy. Trying to go silent now might be futile. And besides, the desire to communicate, to reach out, to understand others, is fundamental to human nature. It's hard to imagine a scenario where humanity discovers that we're not alone and then remains silent out of fear. The compulsion to connect would probably overcome the caution. These are the conversations happening in research institutions, in government agencies, in think tanks and policy centers. Not widely, not publicly, but seriously. Because the scientific community has realized that fast radio bursts might not just be an interesting astrophysical phenomenon, they might be the most important discovery in human history, and they're taking that seriously. They're preparing, they're thinking, they're gaming out scenarios, and they're quietly waiting for the moment when they can point to a signal and say with confidence, this is artificial, this is a message from an intelligent civilization, this is proof that we're not alone. So what are scientists actually doing right now to figure this out? What's the concrete work happening in research institutions around the world? world. Because it's not just theoretical speculation. There are real people doing real work every single day to understand fast radio bursts and to develop methods for distinguishing artificial signals from natural phenomena. Let me walk you through what that actually looks like in practice, because the methodology matters. Understanding how scientists are approaching this problem matters. The first thing you need to know is that there are now dedicated telescopes specifically designed to detect fast radio bursts quickly and efficiently. CHIME is the primary one. It's a weird-looking instrument. It's not a traditional dish antenna. Instead, it's 4 cylindrical parabolic reflectors arranged in a line. It looks more like a series of bicycle racks than a telescope, but it's incredibly effective. It can scan about half the entire sky every day. It can observe while other things are happening. It can detect and localize bursts in real time. When a burst is detected, alerts go out to other observatories worldwide within seconds. The goal is to catch the afterglow, to see what's happening at the location of the burst across multiple wavelengths: radio, infrared, visible light, X-rays, gamma rays. If you can observe the same location with multiple instruments, you get a complete picture of what's happening. CHIME has a team of operators and researchers monitoring the data 24 hours a day, 3 shifts, constantly watching for new detections. And when they find something interesting, something unusual, the alert system springs into action. Automated emails and messages go out to astronomers all over the world, at the European Southern Observatory, at observatories in Australia, in Japan, in China, in South Africa. Within minutes, dozens of telescopes are being pointed at the location where the burst originated. Everyone wants data. Everyone wants to understand what happened. And that coordination has led to incredible discoveries. It's also led to the development of protocols for rapid response, which is exactly what you'd need if you suddenly detected something that looked artificial. You'd want the best data from the most sensitive instruments. You'd want multiple independent observations. You'd want verification. The analytical methods being used to study fast radio bursts have become incredibly sophisticated. Researchers aren't just looking at whether a burst happened, they're analyzing the fine structure, the microstructure of the signal. How does the intensity vary across the millisecond duration? How does the frequency sweep? Does it sweep upward or downward? What's the shape of the pulse at different frequencies? Are there harmonics? Are there subpulses? Does the polarization change during the burst? All of these details contain information about the source, information about what's happening, and machine learning algorithms are trained to identify patterns in these details, patterns that might indicate artificial origin versus natural phenomena. One of the key diagnostic tools is something called the dispersion measure. We've talked about this before. It's the amount that the signal gets spread out by traveling through the interstellar medium. But here's what's interesting about it in the context of artificial signals. The dispersion measure is unique. It's a fingerprint of the signal's path through space. You can calculate how much dispersion a signal would have based on its distance and the density of electrons it passed through. And if you're clever enough, you can create signals that compensate for dispersion automatically. You can encode the message in such a way that when it arrives at a distant receiver, the dispersion actually enhances the signal rather than degrading it. It's like pre-correcting for distortion. It's something an engineered system could do. A natural phenomenon probably wouldn't. Researchers are looking for other signatures too: repetition patterns, periodicities, mathematical relationships between bursts. If you receive multiple bursts from the same source, you can look at the times between bursts. Are they random? Are they clustered? Are there patterns? Some repeating bursts show periodicities that are almost too perfect, too regular, like they're following a schedule, like something is turning on and off according to a predetermined rhythm. That's suspicious. Natural phenomena don't usually follow schedules. Explosions are chaotic. Accretion processes are turbulent. But if you're transmitting a signal deliberately, you'd want to repeat it on a schedule. You'd want it to be predictable. You'd want observers to know when the next pulse is coming. There's also work being done on signal coherence. How much of the signal maintains its structure as it travels across billions of light years? Coherence is actually a big deal. Signals naturally lose coherence as they travel through space. The signal gets scrambled. It gets mixed up. If you can measure how much coherence is maintained, you can learn about the signal's history, about what it's been through. And here's the interesting part. Some signals maintain more coherence than you'd expect. They seem almost designed to maintain their integrity, as if the signal was specifically engineered to survive the journey through billions of light years of noisy interstellar space. International cooperation on FRB research is actually remarkable. It transcends national boundaries in ways that are rare in science. Scientists from China and the United States collaborate. Europeans work with Australians. Researchers from India contribute to projects led by Canadian institutions. There's a real sense in the community that understanding fast radio bursts is important enough to put aside competition and work together. Part of that is just scientific curiosity. Part of that is recognition that if something significant is discovered, everyone will benefit. But part of it is also the unspoken acknowledgement that if these signals are artificial, It's a human discovery. It belongs to all humans, and figuring it out requires humanity working together. There are regular conferences, symposiums dedicated entirely to fast radio bursts. The annual Fast Radio Burst Symposium brings together the leading researchers in the field, hundreds of scientists presenting papers, discussing findings, debating interpretations, sharing data. The amount of data being shared is actually unprecedented. In many fields, data is hoarded. Researchers keep their data sets private to maintain competitive advantage. But in FRB research, most of the major observatories have committed to releasing their data publicly, making it available to researchers everywhere. Any astronomer can download raw CHIME data, can download Parkes data, can download VLA data, can run their own analyses. This democratization of data has accelerated the rate of discovery. Because you get many eyes on the same data, you get different perspectives. You get people thinking about the data in ways that the original researchers didn't think about it. The databases storing FRB information are now massive. Thousands of bursts catalogued, with detailed information about each one: location, time, duration, energy, polarization, dispersion measure, everything. These databases are searchable. Astronomers can query them looking for patterns, looking for relationships between bursts, looking for anomalies. There are projects dedicated to searching the database for signs of artificial signals, looking for patterns that don't fit natural phenomena models, looking for mathematical relationships that might indicate intentional design. So far, nothing definitive has been found, but the search is ongoing. It's systematic, it's rigorous. One of the most interesting developments in recent years has been the application of machine learning to the problem of signal classification. Researchers have trained neural networks on large data sets of known bursts, teaching the networks what natural FRBs look like, what their characteristics are, what makes them normal. Then they feed the network data from new bursts and the network tries to classify them. Does this look like a normal burst? Or does something seem off? The advantage of using machine learning is that the networks can detect subtle patterns that humans might miss. They can process massive amounts of data incredibly quickly. They can identify outliers, anomalies, bursts that don't fit the normal distribution. These outlier bursts then get extra scrutiny from human researchers, get analyzed in detail. Could be nothing, could be instrumental artifacts, but could also be something unusual, something worth investigating further. There's also been work on developing better methods for localizing bursts, for pinpointing their exact locations in the sky. The more precisely you can locate a burst, the more information you have about its source. CHIME's localization is good, but not perfect. There are new technologies in development that will do better. Interferometric techniques, arrays of radio telescopes spread across continents acting as a single instrument. These will be able to locate bursts with arc-second precision or better, which means that astronomers will be able to identify exactly which object produced the burst. Is it a pulsar? Is it a black hole? Is it a magnetar? Is it something else entirely? Having precise localizations will answer a lot of questions about the sources. The square kilometer array is particularly important here. The SKA is going to be revolutionary for FRB science. It's going to be orders of magnitude more sensitive than current telescopes, which means it will detect much weaker bursts. It will detect fainter sources. It will pick up signals that current telescopes would miss entirely. When the SKA comes online, probably in the late 2020s, everything is going to change. The rate of discovery will increase dramatically. The quality of data will improve, the precision of measurements will be better, and that could be the game changer. That could be the point where patterns become undeniable, where artificial signals become obvious, or where natural explanations become so compelling that the mystery finally gets solved. There's also work happening on theoretical models. Physicists are running simulations, trying to understand how different phenomena could produce fast radio bursts, running the numbers to see if magnetars could actually work, if black holes could work, if neutron star collisions could work. They're trying to figure out the limits of what natural phenomena can produce, and they're finding that natural phenomena can produce a lot, can produce the energy levels, can produce the time scales, can produce bursts that have the characteristics we observe, but they can't produce all of them, not all together, not in all the configurations we see. There's always something left unexplained, always some observation that doesn't quite fit the model, and that's where the conversation gets interesting. Because when conventional models fail, when natural explanations come up short, physicists have to ask themselves what that means. It means either one of two things. Either we're missing something fundamental about how the universe works. Physics is incomplete in some important way. There's physics we haven't discovered yet, or the phenomenon we're observing isn't natural, it's artificial. artificial, it's produced by technology. Both possibilities are profound. Both require rethinking our understanding of reality. And that's where the scientific community stands right now, at this inflection point, knowing that something important is happening, knowing that we're close to understanding what it is, but not quite there yet. The social dynamics within the FRB research community are also interesting. There's a split forming, not an official split, not publicly acknowledged, but a split nonetheless. On one side, there are researchers who are committed to finding natural explanations, who believe that no matter how weird these bursts are, they're ultimately caused by exotic but natural phenomena, who think that proposing artificial origins is premature. On the other side are researchers who are genuinely open to artificial explanations, who think that the data warrants serious consideration of that possibility, who think that scientists have an obligation to follow the evidence wherever it leads, even if it leads to places that sound like science fiction. Most researchers are somewhere in the middle. They want natural explanations. They prefer natural explanations, but they're open to other possibilities if the evidence demands it. They're waiting for the breakthrough, the observation that will definitively settle the question one way or another, and they know it could come at any time. The next burst detected could be the one that's so unusual, so anomalous, so impossible to explain with conventional physics that it forces the conversation, forces the scientific community to seriously consider whether what we're looking at is artificial signaling from an extraterrestrial civilization. And here's what nobody says out loud, but everyone is thinking. If that moment comes, if that breakthrough discovery happens, if we detect a fast radio burst that has all the hallmarks of artificial origin, of technological production, of intelligent design, then everything changes. Immediately, the research that's currently fringe becomes mainstream. The hypotheses that are currently speculative become serious research programs. The questions that are currently whispered in hallways become the central focus of science funding. And the conversation about humanity's place in the universe becomes a conversation about whether we're alone or whether we've finally received proof that intelligence exists elsewhere in the cosmos. Now let's think about the trajectory we're actually on, where this is going. Because it's not just about understanding what fast radio bursts are in some abstract scientific way. It's about where humanity goes from here, what the next 5 years look like, what the next decade looks like, what discoveries might be waiting for us, and what we need to be prepared for. The rate of technological advancement in astronomy has been exponential. It's not linear. Each new generation of instruments is orders of magnitude more sensitive than the previous generation. CHIME was a leap forward compared to Parkes, but CHIME will look primitive compared to the SKA when it comes online. And whatever comes after the SKA will make the SKA look quaint. We're entering an era where our ability to detect faint signals from distant sources is increasing rapidly, and with that increased ability comes increased probability of finding something important, something that might actually answer the question we've been asking for millennia. The machine learning algorithms being developed for FRB analysis will only get better. More data means better training. More bursts detected means more examples for the neural networks to learn from. More sophisticated analysis means more subtle patterns can be found. Within 5 years, the analytical capabilities will probably be 2 or 3 times better than they are today. Within 10 years, they'll be revolutionarily better, and that matters, because if there's even a small signal hiding in the data, even a slight pattern that indicates artificial origin, these systems will find it. There's also the matter of international cooperation continuing to expand. India is building the Murchison Wide Field Array Extension, or MWX, which will be sensitive to fast radio bursts. China is building the 500-meter aperture spherical telescope, the FAST, which has already discovered multiple new bursts. Europe is developing the European VLBI network. Japan has instruments in development. The global network of observatories dedicated to FRB research is growing. The redundancy is increasing, and that means that fewer interesting bursts will slip through undetected. Fewer anomalies will go unnoticed. The question of what humanity does with this discovery when it comes is going to depend heavily on political and cultural factors. Different societies will respond differently. Different governments will have different priorities. Some will see it as primarily a scientific achievement. Others will see it as a military or strategic consideration. Some will see it as a religious event. Some will see it as an opportunity for technological advancement. And those different perspectives will shape how the discovery is communicated to the public, how it's handled by institutions, how resources are allocated in response. What we know from historical precedent is that major scientific discoveries don't happen in isolation. They happen in the context of existing knowledge, existing technologies, existing frameworks for understanding the world, and they changed those frameworks. When Copernicus showed that the Earth orbited the Sun rather than the other way around, it created a crisis in European society. It forced a reckoning. Eventually, society adapted. We adjusted our understanding, and we moved forward. The same thing will happen with confirmation of extraterrestrial intelligence. Eventually, we'll adapt. But there will be a period of adjustment, a period where the world feels fundamentally different. That adjustment period could take months or years. During that time, you might see disruption in financial markets. Not because anyone's arguing about the science, but because fundamental uncertainty about humanity's position in the universe makes investors nervous. You might see disruption in religious communities as different faith traditions grapple with what extraterrestrial intelligence means for their theology. You might see a shift in political priorities as governments recognize that this changes everything. You might see an explosion of scientific funding for space exploration and development of better telescopes and contact protocols. But you might also see something more profound. You might see a moment of clarity, a moment where humanity realizes that despite all our divisions, despite all our conflicts and differences and competing interests, we're all humans. We all share the Earth. We all share the same cosmic heritage. We're all members of one species on one planet in a universe that's full of other intelligences. That realization could be unifying. It could be transformative. It could lead to a new era of global cooperation, or it could trigger conflict as different nations compete for advantage. History shows us that major changes in human understanding can go either direction. The scientific discoveries that will come after confirmation of extraterrestrial signals will be accelerating rapidly. Once you know that intelligence exists elsewhere, you start looking for evidence more carefully. You start asking different questions. You look at radio signals differently. You look at anomalies in existing data that you'd previously dismissed. You might find that signals we'd ignored for years were actually artificial in origin. You might find that there are patterns in the cosmic microwave background that indicate previous civilizations. You might find evidence of megastructures or engineering projects that span galaxy-size scales. Each discovery will lead to more questions. Each answer will suggest new areas to investigate. There's also the question of future preparation. Right now, if we detected an artificial signal, we'd have to figure out how to respond as we go. We don't have protocols in place. We don't have agreed-upon messages. We don't have infrastructure designed for interstellar communication. All of that would have to be invented rapidly if the need arose. But some researchers are arguing that humanity should start preparing now, should start thinking about what our response should be, should start developing the technical infrastructure for potential communication, should start having conversations about what humanity wants to say to any civilization that might be listening. There's the question of disclosure timing. How quickly should the public be informed after confirmation of extraterrestrial signals? Should governments take time to analyze the discovery? Should they brief world leaders first? Should they get input from international organizations like the United Nations? Should they consult religious leaders? Or should they immediately announce it to the world and let everyone process it together? Different people have different opinions. Some argue that the public has a right to know immediately, that any delay is a cover-up. Others argue that careful, measured disclosure prevents panic and allows institutions to prepare. It's a genuine dilemma with no perfect answer. The economic implications deserve more attention than they usually get. Confirmation of extraterrestrial intelligence would probably lead to massive investment in space exploration, in developing better detection systems, in preparing for potential contact. That investment would create jobs. It would drive innovation, but it would also disrupt existing industries. Space technology companies would suddenly be worth vastly more. Defense contractors might see increased funding if governments view this as a security concern. Energy companies might face disruption if extraterrestrial knowledge makes current energy sources obsolete. Education would shift as schools incorporated the new understanding of humanity's place in the cosmos. Everything from entertainment to food production could eventually be affected as society grappled with this new reality and reorganized around this knowledge. There's also the possibility that this discovery would lead to a fundamental change in how humanity sees itself. Right now, we see ourselves as divided by nation, by ethnicity, by ideology, by religion, by economic status, and all of those divisions matter. They shape our politics and our conflicts. But from a cosmic perspective, all those divisions are superficial. We're all humans on a single planet in a single solar system in a single galaxy, an incredibly insignificant speck in an incomprehensibly vast universe. If confirmation of extraterrestrial intelligence could make that perspective visceral for people, make that understanding real in their minds rather than just intellectual, it could be transformative. It could change how we treat each other, how we think about war and conflict, how we think about our shared future. But there's a flip side to that optimism. Contact with extraterrestrial intelligence could also be disturbing, could bring bad news. What if the signals are warnings? What if other intelligences in the universe are telling us about threats we don't know about? What if they're warning us about black holes or asteroid impacts or cosmic catastrophes? What if they're telling us that intelligent civilizations have limited lifespans, that most civilizations self-destruct, that the universe is hostile, that cooperation between different intelligences is rare or impossible? That would be a different kind of discovery, still profound. still world-changing, but frightening rather than inspiring. The question of what happens next in FRB research is going to determine whether we get answers soon or whether this remains a mystery for decades. The SKA will be transformational when it comes online, but there might be breakthroughs before that. There might be discoveries using current technology that suddenly illuminate the picture. There might be a repeating FRB that we can monitor so carefully that it reveals its mechanism. There might be an associated signal across multiple wavelengths that gives us data we can actually interpret. The next breakthrough could come tomorrow, or it could come years from now, but it's coming. The scientific community is convinced of that. The rate of discovery is accelerating. The questions are being asked. The data is being collected and analyzed, and eventually we'll have answers. The role that artificial intelligence and machine learning will play in this discovery cannot be overstated. AI systems are already finding patterns in FRB data that humans would miss. AI is already classifying bursts in ways that are more efficient than human analysis. As AI gets more sophisticated, as the algorithms get smarter, as the training datasets get larger, AI might be the system that makes the actual breakthrough discovery. An algorithm might find the pattern that proves artificial origin. An AI might notice the anomaly that makes it obvious. An AI might recognize a signal structure that indicates intelligence. And that's an interesting thought, that the discovery confirming humanity is not alone might be made not by a human, but by a machine, made by technology we've created, made by the tools we've built to understand the universe. And here's what that means. It means we're entering a new era of discovery, an era where we have the tools to detect extraterrestrial signals if they exist, an era where the theoretical possibility of finding evidence of other intelligence is becoming practical reality, an era where the ancient questions about whether we're alone are shifting from philosophy into empirical science. These are questions that can now be answered through observation and analysis and data, and that makes this moment unique in human history. For the first time, we have the capability to actually answer these questions. We have the technology, we have the instruments, we have the analytical methods, we have the international cooperation. We have everything we need. All we're missing is the discovery itself, and that could come at any moment. Let's go back to where we started. September 3rd, 2024, Perth, Australia, 3 in the morning. That astronomer staring at her screen, watching a signal repeat every 3 minutes, perfectly, predictably. She didn't know what it was. She still doesn't. Nobody does. But she knew it mattered. She knew something important was happening, and she reached out to colleagues. She shared the data. She became part of a conversation that's still happening. That's happening right now. That might lead to the most important discovery in human history. That signal is still repeating, not at Perth anymore. The source is still out there, somewhere in a distant galaxy, billions of light years away. Something is still sending those pulses, still following that 3-minute rhythm, still transmitting. And telescopes around the world are still listening, still recording, still analyzing, still searching for the pattern that might explain what it is. And here's the thing that's remarkable about that. We don't know what we're listening to. We might be listening to the death throes of a collapsing star. We might be listening to the signature of exotic physics we've never encountered before. We might be listening to a message from an intelligence that exists billions of light years away, from a civilization whose light and radio signals we'll never receive, who will never receive our signals, but whose presence we've detected, whose existence we can confirm through this simple fact, that something out there has enough power and enough intention to send a signal that we can detect across the cosmos. The question that started this entire video was simple. Are we alone after everything we've covered? After looking at the physics and the data and the theories and the possibilities and the implications? The answer is still we don't know. We don't know yet, but we're closer to knowing. Every burst detected brings us closer. Every analysis brings us closer. Every discovery brings us closer. And that matters, because the search for that answer has defined human civilization. It's driven our mythology, our religion, our philosophy, our science. For thousands of years, we've asked this question. And for the first time, we have the tools to actually answer it. And the answer might come tomorrow. It might come next year. It might come in 5 years when the SKA comes online. But it's coming. That's what the data tells us. That's what the rate of discovery suggests. That's what the trajectory of technological advancement indicates. When that answer comes, when we finally get confirmation one way or another, when we detect a signal that's unmistakably artificial, or when we finally understand the natural mechanism producing these bursts, everything changes. The uncertainty ends. The speculation ends. We'll have our answer. And then the real work begins. Then we have to figure out what to do with that knowledge, how to respond, how to integrate it into our understanding of ourselves and our civilization. But there's something that's important to understand right now, today, before that discovery comes. We're not passive observers waiting for the answer to reveal itself. Every person who's curious about this, every person who's watching this video and wondering about these signals, every person who's asking themselves these questions, you're part of this. You're part of the process, because the scientific discoveries that change human civilization don't happen in a vacuum. They happen in the context of a culture that's ready to receive them, a culture that's already thinking about the questions, a culture that's prepared to integrate new knowledge into its framework. The fact that you know about fast radio bursts now, the fact that you understand that scientists are detecting signals they can't explain, the fact that you're aware that the answer to whether we're alone might be coming soon, that awareness matters. It changes how you think about the cosmos. It changes how you think about humanity's place in it. It changes how you approach the future, and multiplied across millions of people, across billions of people around the world, that awareness becomes cultural momentum. It becomes the foundation for how civilization responds when the discovery comes. There's also the question of what you should do with this knowledge, what any of us should do with the understanding that the universe is probably full of signals, that intelligence probably exists elsewhere, that we're probably not alone. Some people respond by becoming interested in SETI, by supporting research organizations dedicated to detecting extraterrestrial signals, by volunteering for projects that analyze data looking for patterns. Some people respond by thinking differently about global politics, about whether our conflicts on Earth matter in the context of a universe full of intelligence. Some people respond by thinking differently about religion, by reconsidering their faith or exploring different theological frameworks that incorporate this knowledge. Some people respond by becoming interested in space exploration, by supporting funding for better telescopes and space missions. And some people respond by simply thinking more deeply about what it means to be human in a cosmos that probably contains other intelligences. All of those responses are valid. All of them contribute to cultural readiness for the moment when the answer comes. All of them matter, because when fast radio bursts are finally explained, when we know what they are and where they come from, the conversation won't be just among scientists. It'll be among everyone. It'll be global. It'll be about what this means for us, for our future, for our understanding of ourselves. And the more people who've already been thinking about these questions, the more people who've already integrated this possibility into their worldview, the better prepared humanity will be to respond to that moment when it comes. There are real people working on this right now, real astronomers at real institutions spending their careers trying to understand fast radio bursts, spending nights observing, days analyzing, publishing papers, presenting findings, teaching students, training the next generation of researchers who will make the actual breakthrough discovery. Those people deserve recognition, they deserve support, they deserve funding, because they're working on one of the most important scientific questions, and they're doing it often without public recognition or broad understanding of why it matters. If you're interested in supporting this work, if you want to contribute to the research, there are ways to do that. You can support SETI. You can support astronomy departments at universities. You can volunteer for citizen science projects that analyze astronomical data. You can engage with science education and help other people understand these concepts. You can vote for politicians who support funding for science and space exploration. You can share information like this video with other people. You can have conversations about what these signals mean, what fast radio bursts are, what the implications might be. All of that contributes to the ecosystem of discovery. There's also something profound about the moment we're living in right now. In the next 5 to 10 years, in this specific era of human history, we're at the threshold. We're at the inflection point. We have the technology to detect signals from across the cosmos. We have the analytical methods to determine if they're artificial. We have the global cooperation to coordinate the discovery. We have the internet and communication infrastructure to share findings instantly around the world. None of that existed 50 years ago. All of it is new. All of it is converging on this moment. And it means that if there are signals to be found, if there are artificial transmissions from extraterrestrial civilizations, we're probably the generation that will find them. That's a remarkable thought, that you might be alive during the moment when humanity discovers it's not alone, that you might be a witness to what will probably be remembered as the most significant event in human history, not because you're doing the discovering yourself necessarily, but because you're living through it. You're part of the generation that's connected to this moment, that knows about this question, that understands what's at stake, and that awareness might shape what comes next in ways we can't fully predict. The signal from Perth keeps repeating every 3 minutes. Somewhere out there, still sending, still transmitting, and we're still listening. And we're still trying to understand. And when we do understand, when the mystery is finally solved, the universe will seem like a different place. We'll know something about ourselves that we don't know now. We'll know whether we're alone. And that knowledge will reshape civilization in ways we can anticipate and in ways we probably can't even imagine yet. So here's what I want to leave you with. A question. A real question that you should sit with, that you should think about, that you should discuss with other people. If we detected a signal tomorrow, if astronomers announced that they'd found an artificial transmission from an extraterrestrial extraterrestrial civilization? How would that change you? How would that change how you think about your life, about your priorities, about what matters, about humanity's future? Because that question, that thought experiment, it reveals something about your values, about what you think is important, about where you think we should be heading as a species. The signals are out there, whether they're natural or artificial, whether they're messages or cosmic phenomena. They're real, they exist, we're detecting them, and we're working to understand them. The answer might come soon, it might come after we're gone, but it will come, because the universe operates according to physical laws, and eventually through investigation and observation and analysis, we'll understand those laws, we'll understand what's producing these signals, we'll understand our place in the cosmos, and that moment, whenever it comes, will be historic. Thank you for spending the last 2 hours thinking about this with me. Thank you for considering these questions. Thank you for engaging with ideas that stretch the boundaries of what we think we know about reality. Because that engagement matters, that curiosity matters, that willingness to think about possibilities and implications that matters. Because it's curiosity and investigation and rigorous thinking that will ultimately lead to the discovery, that will lead to the answer, that will lead to the moment when everything changes. If you want to stay updated on fast radio burst discoveries as they happen, if you want to follow the research, if you want to know immediately when something significant is announced, subscribe to this channel, click the bell notification, follow major astronomy publications, follow SETI, follow the researchers doing this work, because the discovery could come at any moment, and you'll want to know about it when it does. You'll want to be part of that moment, that historic moment, that moment when we finally know for sure. Are we alone, or are we part of a cosmos full of intelligence and signals and meaning? The question is still open, the answer is still unknown, but the search is on, and everything we've covered in this video, everything we've discussed, everything that's happening in laboratories and observatories around the world right now, all of it is leading somewhere, all of it is building towards something, all of it is moving us closer to the truth, to the answer, to the moment when we finally understand, and that's worth paying attention to, that's worth thinking about, that's worth being excited about. The universe has been sending signals, we're finally learning how to listen, and what we hear, what we discover, what we learn, that will define the next era of human civilization, that will shape our future, that will answer questions that have haunted us since we first looked up at the night sky and wondered, are we alone out there? The answer is coming, and it's probably going to be more extraordinary than we can imagine.